All right, derivatives of inverse functions. So I found this online by just Googling Desmos and inverse derivative functions, something like that. And this is showing you slopes of tangent lines with the dashed red and blue lines. And if you decide to interact with this, if you go over to f of x and you change that function, it will automatically be graphing the inverse because of what it has set up. So you can look at a variety of functions if you want to play with this later. What I want you to notice is when you're looking at the slopes of these tangent lines, do you see that they are not perpendicular to each other? At least not necessarily. Now, I'm pointing that out because people have a way of accidentally throwing in the issue of perpendicular slopes when the problems we're about to look at show up. How many times did you do negative reciprocal, negative reciprocal, negative reciprocal? How many times have you done that? A lot of times, because that's the problem. You've done it so many times that what I have found is people will accidentally throw a negative sign in when they're reciprocating, even if they're thinking don't do that, because it is so automatic for you because of unfortunate. Anyway, know that you need to be careful with that. And now let's take a moment to look at the idea of inverses. The idea of inverses are your x and y coordinates swap places. That's really the essential nature of a pair of inverses. So let's take a moment to think, what is slope? And I'm looking in chat. What is slope? And how might you write slope as a formula? Slope is change in y over change in x. So what do you think is going to happen if you take all your x's and y's and go whoop-a-boom? What's it going to do? Right. It's going to reciprocate, just reciprocate. And I want you to look at these slopes and I want you to notice both the red dashed line and the blue dashed line have positive slopes right now. If your function has a negative slope at a point, its inverse function also has a negative slope at its corresponding point. Now, this is really important, at its corresponding point. I'm going to zoom in here. And let's take a look at these corresponding points. And I have a very important question. Do those use the same x coordinate? They do not. Now, the idea of when you have a pair of inverse functions and you look at how do their derivatives compare to each other, oh, they're just reciprocals. Oh, that's it. Don't be deceived. People mess up when they think that that's all there is to it. There's an extra problem. And that problem is that while their slopes are reciprocals, they are not reciprocals at the same x value. So if you saw ahead of time that I told you you could print this out, I have this, and I'm going to start going through it. Oh, lag time. Okay. So I'm going to start off with just generic, a pair of inverse functions. What is the derivative formula? So I'm going to start off with, if f is the inverse function for g, let me get my pen going, there we go. then that means that the derivative of g is the reciprocal of the derivative of f. But I do not get to plug x in. This x is an x coordinate for g. I need to put into my f prime, correct. You want to put in the y value. Now, the official formula says if x is g's input, then g of x is the output. G of x is the y value when x is the input. So that means that in here, I have g of x. To be honest with you, I try to not look at this formula. I try to logically think through the problems. And so what I have ready for you is a way that I organize my information, because it's okay, I'm going to admit I have some issues with like east and west. Which direction am I supposed to go? If you have any type of mild dyslexia, this is going to be an issue for you. And if you don't organize it, you're going to find that you go, oh, hey, I need to do this. And then you forget that you did that. And then you do it again. Yeah. Anyway, so this is how I organize problems when they come to me. I first of all look at who are they asking me to find the derivative of, and what is the x coordinate of that function. When I notice that, I'll start a table and I'll say, okay, so the g of x function, I need to be looking at a point that uses that a number as its x coordinate. Then I look at, that means the corresponding point for the inverse function is going to be, let's see it in chat. Yep. And so it's really important that you notice that the x coordinate that matters for f is actually this y coordinate on g, not the a. And if you literally just write these down with the numbers in the problem, because most problems are going to have a be a particular number, then b is a particular number. Now, if you want to know the slope of f at this point, you need to plug in f's x coordinate. So that means that the slope of f that I am concerned with needs to be found by plugging b in to the derivative of f. Now, at corresponding points, the slopes are reciprocals. So literally all you need to do at this point is take f prime of b and reciprocate it. Bam, done. So I'm going to say that g prime of a, which is what you are trying to get to, that is the same thing as 1 over just reciprocal of what was found there. So basically, I'm going to post a printed out version of this worksheet that has everything filled out. And what you'll see is I'll put in the numbers, like start here, number 1, number 2, number 3, and number 4, at least the way that I have it set up. You may find your own way of organizing, but I'm presenting to you a way that you can do it where you are less likely to mess up. So what I want to do right now is have you go to AP Classroom, and let's look at the first assigned problem together. If we are trying to find f prime a, then the slope of f of x would be the reciprocal. If you wanted f prime of a, you would want the reciprocal of g prime of b. And so here you go. Question one. Question one. Do not answer in chat. I remembered this time to say that quickly. Period 1, I look over and a bunch of people have it answered. I'm like, no, you're supposed to give everyone a chance. Yes, I am recording. Oh, wait, am I? Yes, I've got the little record on my Screencastify. Yes, I am recording. Thank you for reminding me, because I don't remember sometimes. Okay, I'm going to screenshot this so that I can do some highlighting. And I'm going to cross my fingers that this will work this time. Period 1, it just said, I don't feel well right now. Come back later. Don't you love it when your computer does that when you need to get something done? It's fantastic. Okay. By the way, I'm trying to right now give you time to read it yourself and see if you can get the right answer. But I need to move because we have limited time. So first thing I'm looking at is, what are they asking me to find? They are asking me to find g prime of 3. So what I will personally do is I will set up, all right, g, and corresponding point. G matters when x is 3. That means the inverse, which I am told right here, the inverse is f. That means that I care about f when its y is equal to 3. Now, I was not told what g's y coordinate was. So now I need to look at the information that's given to me, and I'm going to highlight that. And do you see the trick? The trick is recognizing that you need to be looking at f when it has a y coordinate 3. That means you need to be looking at f when its x coordinate is 6. So when I move over to slope, I know that I need to find f prime of 6. Then I go looking for what's f prime of 6. Then what does that mean? G prime at the corresponding point, the corresponding x coordinate of 3. What must that be? Make sure you don't change the sign when you reciprocate. You have 3 more problems to work on as homework, but I wanted to go through one of those with you to show how you can organize your way through this and get it right every time. So, moving off of that, I'm coming back over here. And that's all you need to know about generic functions and the derivative relationship. Now, inverse trig functions. What are their derivatives? How many inverse trig functions do we have? 6. That means we might have 6 formulas. Lucky for us, we only need to remember 3, and I'll explain why. But we are going to come up with these formulas, and this is going to be so much fun. I'm serious. I'm totally serious. I'm not being sarcastic right now about fun. Okay, if you printed this out ahead of time, then it's nice that you have that in front of you. If not, you know, you can maybe watch the video and fill it out later to help you see getting through this. But I'm going to have to go through it relatively fast, faster than I would like to in a classroom setting. All right, so I've got a triangle ready to go. I am using variable t as an answer to, it is the output of my sine theta function. I'm using a t because I like to stay away from x's and y's when I'm showing things with sine and cosine because people get it all scrambled with the unit circle. So I'm trying to use a variable that is not in the unit circle world. Now, if t is equal to sine theta, then its inverse function would be theta is equal to the inverse sine of t. And the way that I have these variables set up, it's going to compensate for all the issues of the A and B thing that we were looking at, and it's going to run really, really smoothly through. Now, when I look at a right triangle and I see sine, sine is which side over what side? You know that. You can write it in chat. Oh, it rhymes. Sine theta is, yep, opposite over hypotenuse. T is not a fraction. How do I write it as a fraction? Ding! All right. So I can actually create an interactive triangle that tells me 12 functions at once. I'm not kidding you, 12 functions at once. You've got your 6 trig functions and you've got your 6 inverse trig functions. This triangle is like a key to all of them in one problem. So what I can do is I can take this and write it ratio-wise on opposite over hypotenuse. Now, guess what formula gets us the third side of a triangle, a right triangle? Good old Pythag. Yes, Pythagorean theorem. So everyone Pythagorean theorem this into a formula. What is the third side? I'm trying to draw a straight line. To write it in one formula, I need to take the square root of the hypotenuse squared minus the known leg squared. And since 1 squared is just 1, you got it. Now, this gives me all 3 sides of this triangle, and it is actually giving you 12 functions that you can work with. Isn't that cool? I think it's really, 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 really cool. It's a powerful little triangle. Now, the next thing we're going to do is I'm going to ask you, what is the derivative of sine theta? What is the derivative of sine theta? Cosine theta. And I'm going to write it the derivative of t with respect to theta is cosine theta. Now, let's look over at that triangle. According to that triangle, what is cosine theta? Cosine theta is which side over what? Adjacent over hypotenuse. The hypotenuse is 1, so cosine theta is the square root of 1 minus t squared. That means that I can now write dt d theta in terms of t, not theta. And that's what I need to be able to come up with its inverse trig derivative. So here we go. I'm going to, actually, no, not in red yet. This means dt d theta in terms of t is the square root of 1 minus t squared. Now, I'm going to move over to the side of the inverse trig function. And I want to ask, what is the formula for the derivative of the inverse sine of t? In other words, what is d theta dt? And with d theta dt, and you see it in the formula even, it is the reciprocal of dt d theta. But I'm referring more to the formula that we got earlier than I am to the algebra that this looks like. And now I am actually ready to say the answer, if I can get it to stop doing that. D theta dt is equal to 1 over dt d theta. Voila. That is a formula, and you need to memorize this formula. But I want you to look at the triangle. Don't just flat out memorize this formula. See it through the triangle, and you will remember it far better. These formulas are going to come back in BC calculus. If you're just on the ride of the AB course, you just need to know these formulas and be ready with them. Now, I want to point out real quick while I'm at it. If t had been cosine, the difference between these triangles would be that the two legs would swap sides. And here I started with sine and I got derivative cosine. If I start with cosine, what is the derivative I get? I get negative sine. Now, with these two switched and these legs switched, I'm going to still end up with the same formula, but times a negative 1, because the derivative of cosine gives me negative sine. So if you know the derivative of inverse sine, the derivative of inverse cosine is the same exact formula times negative 1. Therefore, you don't really need to memorize an additional formula. And that's why you only need 3 of these. All right, next. Let's do it again, but for tangent. I'm going to start by drawing the triangle. Tangent is what side over what side of a right triangle? Looking in at the chat. Ooh, sip of coffee. I think we type the word app more than we do op. Okay, so tangent theta is opposite over adjacent. So if tangent theta is equal to t, then it is equal to t over 1, opposite over adjacent. Let the Pythagorean theorem find you your third side. If you're watching the video, you can pause the video, but I've got to go faster than that. So Pythagorean theorem will give me the square root of leg squared plus leg squared. And you can either write t squared plus 1 or 1 plus t squared, whichever. The next thing we're going to do is look at what is the derivative of tangent theta. So first, just think, tangent theta, what's the derivative? Derivative of tangent theta is all right, secant squared theta. And that is the derivative of the t function with respect to theta. Now, secant squared is the secant of theta squared. What is the secant of theta? It's cosine's reciprocal. So if it's going to reciprocate cosine, which is adjacent over hypotenuse, then this is hypotenuse over adjacent. And then looking at theta, hypotenuse over adjacent will end up being the Pythagorean theorem result divided by 1. So that means that dt d theta is t squared plus 1, all on its lonesome, no square root, because the derivative of tangent gives me something that is squared. Let that help you in your memorization process. Now, I know that the derivative of inverse tangent is the reciprocal of the derivative that I got from tangent. But the derivative I got from tangent not in terms of theta, in terms of t. And since we found that already, we are ready to write the official formula. The derivative of inverse tangent is 1 over t squared plus 1, no square root. 1 plus t squared if you prefer. There you go. Isn't that beautiful? And then just to say it real quick, if I had done this with cotangent, then these two legs would simply swap. I'd still get the same formula out of Pythagorean theorem, but my derivative would have been a negative cosecant squared. The cosecant squared with these two swapped, I'm going to get the same exact formula. But because the derivative of cotangent gives me a negative cosecant squared, I'm going to get an extra negative sign. And I don't really need to memorize another formula. We have one more to do. Who's having fun? Good. I'm glad I saw a couple of happy people. But this This is really, really exciting to be able to see why these formulas come out instead of just getting a list of formulas to memorize. All right, here we go. Secant. First of all, secant theta is what side over what side on my right triangle? Because it is the reciprocal of cosine, it is hypotenuse over adjacent. And it is equal to t divided by 1. So hypotenuse and adjacent. Now, Pythagorean theorem. What is the third side? It is the square root of hypotenuse squared minus legs squared. Now, what's the derivative of secant theta? Just boom, what is it? Derivative of secant theta is secant theta times tangent theta. That is my dt d theta. Now, let's go over to the triangle to figure out what is secant theta and what is tangent theta. Or I could save my time and go, secant theta is t. But just to kind of use the triangle, secant is hypotenuse over adjacent. What is tangent theta? If it's opposite over adjacent, then it is the square root we got from Pythagorean theorem over 1, or just that square root. So the derivative of dt d theta with respect to t is t times the square root of t squared minus 1. Now, some textbooks are going to put an absolute value on the t, some won't put an absolute value on the t. That is not of your concern at this point, not in an AP calculus class. You just need to remember this formula. But a way to remember this formula is to remember the derivative of secant theta. Secant theta's derivative is secant theta times tangent theta. So you get itself multiplied by something that Pythagorean theorem has to produce for you. Also keep in mind that secant and cosecant both start with hypotenuse over something. So when I say secant theta equals t, that means the hypotenuse gets to be t. And when you Pythagorean theorem, the hypotenuse has to lead the subtraction in Pythagorean theorem. It's got to be the square root of the hypotenuse squared minus the other known leg squared. And just kind of getting that into your head will help you to remember this formula and not mix it up with the other ones. Now, we're almost done. That means if I want to find the derivative formula for inverse secant, I need to find the reciprocal of the derivative that I got from secant, but not in terms of theta, in terms of t. It's set up with that triangle to get to that result faster. So the official formula of the derivative of inverse secant Dun, da, da, dun. And if I had to look at cosecant, the derivative of cosecant is what? I'm hoping you're thinking it or saying it. Derivative of cosecant is negative cosecant theta cotangent theta. And I'm hoping you will see that you're going to end up in the same exact boat, but times a -1. So, the formulas. Snapshot of your textbook. Make sure you know the derivative formulas for inverse sine, inverse tangent, and inverse secant. The others, just be aware that they are the negative of their co-partner. Now, we need to practice doing derivative. But before I even go into practicing, I want to talk about your textbook chose to start with something that's going to mess people up big time, because we're trying to take that elephant in the room and just present it. This is our problem. Okay? I need to say a few things about this. You don't need to write this down. I am talking to you about notation. Now, I don't want to say that mathematicians are lazy. Mathematicians are time efficient, okay? Time efficiency, not lazy. So I'm guessing that perhaps they got tired of writing, say, big parentheses around a trig function, squared or cubed or whatever power they happen to be working with. And, they talked with each other a bit, I'm assuming, and went, could we just do this? Can we all just agree? Because I'm really sick of writing these parentheses, aren't you? Oh, yeah, I'm so sick of writing the parentheses. Yeah, let's do that. Yeah. Trying to make a female voice in there by going, yeah. Because there were female mathematicians out there. They just weren't recognized yet. Anyway, so that choice was made. Now, completely separate from that, having nothing to do with it at all, inverse functions. Now, the first inverses that we look at are pertaining to addition, subtraction, multiplication, division. When we think about a multiplicative inverse, what is a multiplicative inverse? What is if you are multiplying by something, how do you find the inverse, the undoer of that multiplication? And it is multiplication by the reciprocal. Now, naturally, what came out with exponents in exponent rules, what naturally came out, that meant the same thing as reciprocal. I'll just put reciprocal of b. While it is 1 over b, we also write it as b to the -1. That -1 that they use for inverse symbols did originate from the number -1. And it did originate in the position of an exponent. Unfortunately, somebody said, hey, let's use that for the inverse symbol. And so they said, oh, great, I like that idea. That's a nice symbol to use. And we'll put it in the spot of an exponent, just like the multiplicative reciprocal. I'm just making this up, but I'm imagining what these mathematicians might have said to each other and go, oh, there you go, perfect. That means inverse, which the idea of inverse includes a much broader idea than just multiplicative inverse. So now, putting this together, they decided, hey, how do we want to write inverse sine? Anyone? How do we want to write inverse sine? Just use the inverse symbol. Oh, good idea. There we go. Yay, there's inverse sine. What do you guys think? Perfect. I like it. I'll use it too. And then maybe somebody said something. Perhaps they weren't heard. Don't we already use that for like the positive exponents? And, is this a good idea here? And I don't know, maybe it was the one that everybody just thinks is the nerd of the nerds and they can't listen to them because they just, I don't know. But there you have it. You have to be very, very, very careful. This will bite you at some point. You have to understand that, yes, this means inverse sine. And yes, this means the sine of x squared. But this does not mean the reciprocal of sine. What's the reciprocal of sine? Cosecant. Are the functions cosecant and inverse sine, are they very different? Like extremely different? Yeah. Cosine takes in angles. Inverse sine gives out angles. Let's just start with that. So be very, very careful. What they gave you in part A was meant to throw that elephant out there. And let's deal with it. So do know also that somebody along the line went, you know what? People are getting so confused with this notation you chose. How about we use this instead? And then I imagine people going, oh my gosh, why didn't we do that in the first place? And then other people being like, but I like my -1. I use it and I like it and I'm not going to stop using it ever. And so now we are stuck. We use both. Let's not make the problem better. Let's make it more complicated. So you now have to be aware that they mean, these two mean the exact same thing. There are just two different ways of writing it because somebody realized that this was a bad idea, but the people who were using it were not willing to let go. Which is a little bit behind why we still use the imperial system of measurement instead of the metric system. But I don't understand what 65 miles per hour is in the metric system. I'm going to be too confused. We're going to confuse the grandparents and they're all going to go the wrong speed. All right, anyway, I have no more to say. Let's do derivatives. I'm going to erase all of this. And if you're videotaping, you can do a screenshot. And now I am erasing. All right, here we go. If you decide you're going to chain rule this, then you're going to write inverse sine to the power of -1, and that -1 means a power. I don't want to do that. That's going to mess us up. Let's do quotient rule. When you have a constant in the numerator and you do quotient rule, you should do quotient rule quickly. When we start off with low D high, what's D high? 0. You don't need to write 0. I'm going to write 0 so that you're clear. So if you have a constant numerator, instead of turning to the chain rule and dealing with negative exponents, you can start with low D high is 0 minus, and then go high times D low. And don't even write the times 1 yourself. I'm writing it to make sure you're clear. I'm going to come back to that. I'm going to finish the quotient rule. Unfortunately, expressing the inverse sign of x squared, you can't just change that -1 to a -2. Now, inside this parentheses here, we are going to focus on needing to take the derivative with respect to x of inverse sine of x. And that's a formula. What is that formula without looking it up? Now, I'm just going to really quickly rewrite this. Rewriting it, I'm going to end up with a -1 in the numerator. I'm going to have to just stick with inverse sine squared and then times this lovely square root. This is not pretty in any way. And if you want, you can instead use arc sine instead of writing sine to the, not to the, the thing that looks like sine to the -1. Anyway, there we go. Done deal. Let's do the next problem. So I have x times arctan of root x. I'm going to scoot this over. And you know we need to start off with the product rule. I want to be careful that I don't forget I'm in the middle of a product rule. So I'm going to write first times derivative of second, come back, plus derivative of x with respect to x times keep the second function. All of this is going to be the result of the derivative with respect to x of arctan of root x. Now, as you look at, I need to take the derivative of arctan of root x, you should first notice, look at the cute little baby. I feel really bad for all the people trying to work full-time with an infant in their home. Oh my goodness. Okay. Here we go. What is the formula for the derivative of arctan of blah, or inverse tan of blah, whichever way you want to say it? What is the formula for the derivative of this inverse function? And hopefully you remember it is 1 over blah squared plus 1. And again, blah just stands for where the variable normally is and whatever happens to be in that position. So now I'm going to take that baby function and I'm going to give mommy her baby. And then I'm going to multiply by the derivative of root x. And then the derivative of root x is 1/2 x to the negative 1/2. And let's look at how that simplifies. So as far as numerators go, I have this x out here. I have a 2 that's going to go in a denominator. I have an x to the negative 1/2 that will turn into the square root of x in the denominator. And then I have this entire piece. And the square root of x squared. Technically, it's the absolute value of x. We're not going to worry about that at this moment. And then the plus 1. I can simplify this a little bit more. I have 5 minutes left of class. Do you see how that will come together and simplify? A little bit of exponent rules. What about the arc? Thank you. I even wrote it and I still forgot it. And so simplifying this, we're going to end up with the denominator being just 2 times x plus 1. And x divided by root x will end up being root x. Because it's x to the 1 divided by x to the 1/2 becomes x to the 1 minus 1/2. Woohoo! Now, I know you have homework questions, and I was actually thinking what might be best is if I make a video of going through those problems and have it be separate from this one. So I'm going to stop videotaping